Great. Now that we've got the size of the atom, it's time to get the energy of the atom. And the basic idea for this is, well, we can simply use our energy expression, which I think we better copy for ourselves down here. Where was he? It was our standard confinement energy minus the Coulomb part of the interaction. So you recall energy then is our confinement energy, which we said was h bar squared over 2m delta r squared minus our Coulomb energy, Coulomb's constant E squared times 1 over delta r. Now, a little bit of math organization always helps. This first term we already evaluated previously when we talked about the electron localized to a box the size of the hydrogen atom. So we know numerically this is going to have a value of 13.65 electron volts. We've already evaluated that. So since that's a known quantity, what I want to do is to write my result in terms of my known quantity. So I'm going to factor out this term, h bar squared over 2m delta r squared. And then I'll write 1, right? Because that then will account exactly for my first term. And now I'm going to put something here in my parentheses that allows me to recover my second term. Now for the second term, the pieces that I want to have Coulomb's constant E squared times 1 over delta r. From the outside part here, though, I've got 1 over delta r squared, which is too many delta r's in the denominator. So I better put a delta r on top. And if I were to do that, then I know this quantity, when I multiply through here, will give me my Coulomb's constant E squared over delta r. But I also get this pesky h bar squared over 2m that I don't want, so I should multiply by 2m and divide them by h bar squared. And that is an equivalent expression for my energy. Now here's the interesting thing about this, though. I want you to look at this term, right? This has to have units that match. In the end, this times delta r has to have no possible units. That tells me this thing has units of 1 over distance. And this quantity should look very familiar to us. It's h bar squared over twice the mass times the Coulomb pieces. And that's exactly delta r, is h bar squared over the mass times all of the Coulomb pieces. So this circled quantity is actually exactly 1 over delta r. Oh, I'm sorry. 1 over delta r. Delta r, I'm sorry, did not have any factors of 2 in it. So I shouldn't have included the 2 when I circled that. It is just these pieces. So those pieces cancel out with the delta r perfectly. And I'm just left inside with 1 minus 2. Now there are 2 comments I want to make about that. The first is that the 1 is proportionately, of course, associated with the kinetic energy, right? That came from my confinement energy. The 2 here, right, that was associated with the Coulomb energy. That is associated with my potential energy. And what we're seeing here is that the potential energy in the system is exactly coming out. It's coming out proportional to minus 2 as opposed to 1. It's coming out as exactly minus twice the kinetic energy. And this is a famous result that you see all the time in orbital problems. It's a consequence of something known as the virial theorem. It turns out that this is true exactly in classical orbital mechanics, that the average kinetic energy minus twice the average kinetic energy is equal to the average potential energy. So that's kind of cool. That's like a little teaser for something that happens down the road in the class. And I'll also point out that this is true also quantum mechanically. And it's true even if you have many electrons whizzing around inside of an atom. It's a very a powerful theorem that we'll be able to prove a little later on in the course. So that was just my first comment. That's a bit of a side comment, so I'll put a little bubble around that. The more on this original stream of thought is that, well, 1 minus 2 now, that's an easy number. That's minus 1. So the energy then is going to be minus h bar squared over 2m delta r squared. and that numerically equals then exactly minus this first quantity, right? It's just minus of that, minus 13.65, and that in electron volts, and that actually is the known lowest energy state, or known so-called ground state for the hydrogen atom. So that's beautiful too, right? This whole thing is really holding together very nicely. Now, again, as I've said, right now this has been an order of magnitude estimate. It's somewhat of a coincidence that we got exactly the right values. In real life, that was just a little bit of luck. This could have come out to be twice as big or twice as small, but still it's remarkable to get the orders of magnitudes. Now, the final thing I would like to do is to not only just give you the numerical value, but to get the official energy value for you here in terms of the fundamental constants. In other words, I just need to substitute in my delta R squared. So the energy is minus h bar squared over 2m times 1 over delta R squared. So I'm going to put 1 over delta R in here. And then I'll simplify. So we'll have the energy in terms of all fundamental constants. Delta R was, here he is, it's h bar squared over the mass times the Coulomb pieces. So the inverse of that will be mass times Coulomb pieces over h bar squared. So I have mass times the Coulomb pieces, times the Coulomb pieces divided by h bar squared. So then I can work this through now. You can see the Coulomb pieces, there's nothing that's going to cancel or mess with those. So I'm going to get the Coulomb constant times E squared quantity squared. So I've taken care of these terms. The mass will become squared, but then I'm dividing by mass, so I'm left with just one factor of mass on top, and I've taken care of the insides and the outsides. Likewise, h bar squared is squared on the bottom, but then when I multiply by an h bar squared on top, I'll be left with 1 h bar squared on the bottom. And finally, there's this factor of minus 1/2 that comes out in front. So minus 1/2 times that quantity. And that then is our result for the ground state energy of the hydrogen atom, all in terms of the fundamental constants. And we've now solved for the hydrogen atom, at least from order of magnitude perspective, using this very simple but very powerful Heisenberg uncertainty principle. And along the way, I believe we've learned quite a lot of useful information about the interplay between the particle distributions in space and in terms of momentum. And that will conclude our discussion for this particular example.